In this video, I'm going to discuss the third of Maxwell's equations. So this one is usually written as number 3. It's Faraday's law of induction. It's also called the Maxwell-Faraday equation, and sometimes it's given the name of Faraday's law of induction, or even Lenz's law. So Lenz's law is actually a qualitative description that is encompassed inside of Faraday's law. So that's what this video is about. It's about Faraday's law in all of its intricate different naming conventions. So first of all, we're going to look at the integral form, and then we're going to use Stokes theorem, or the curl integral theorem, to convert the integral form of Faraday's equation into the differential form. And then we're going to examine some intuitive properties of this fundamental law. So it is one of Maxwell's equations, and Maxwell's equations are used to describe electromagnetism. So Maxwell's equations form the fundamental basis for all of the classical electrodynamic descriptions of the universe. So anything that's classical mechanics and electromagnetism, it's going to be described by Maxwell's equations. So what is this guy actually saying? What do we have on the left-hand side, and what do we have on the right-hand side? On the left-hand side, we have a line integral along a curve C. And you can see there's a little circle around this integral, so that means it's a closed integral. So it's going around a closed curve. And that closed curve we're going to call C. Sometimes you might see a slightly different notation. Sometimes you might see a partial derivative little d and then s. So I'll write that over here. You might see something like this. And that's just indicating that it's the boundary of a surface. So this guy is just the standard little curly d that you see in partial derivatives as well. And this over here, this is a surface S. So what's this on the right-hand side? Well, we have a surface integral. And we have, in this notation, we have two integrals to indicate that it's a two-dimensional integral. We're integrating over a surface. And what happens when you integrate a vector field over a surface? Well, you get the flux through the surface. So the flux is actually a surface integral of a vector field. And that is actually what this little chunk over here, this integral, is the flux of the magnetic field through a surface. And the boundary of that surface, what we're doing on the left-hand side is we're taking a line integral of the electric field along that boundary. Now this thing over here is sometimes called the electromotive force. And Faraday, when he was discovering a lot of these laws, he actually called this the electromotive force. Sometimes it's called EMF. And in this form down over here, see this red equation, we have epsilon over here, that's the electromotive force. That's the negative of the time derivative of the magnetic flux. Now I want you to let this sink in and see that this form is actually the same as this. But Faraday, he didn't have the mathematical background that Maxwell did. So what Maxwell did is he put together all these ideas from Gauss, from Faraday, and Ampere, and he combined them into a set of 4 equations that are excellent at describing classical electromagnetism. So let's have a look again at this integral form. What do we have? We have vector quantities. E, the electric field, that's a vector quantity. It has a little arrow above it. B, that is the magnetic field. The B field is the magnetic field. Again, it's a vector quantity. This little dl, that is a tiny little segment of the curve. And if we were to look at a curve like this one, a closed curve that sits somewhere in 3D space, it's a one-dimensional object. If you take a tiny little chunk along here, you can call that dl. And it's a vector quantity. So this is a little arrow, drawing a little arrow. That's a tiny little arrow. I'll try to make that a little bit more clear. And at every little point, you can find a little dl that goes around. So there is a directionality associated with this. You're going around the loop in a certain way. If you go around the loop in the opposite direction, you're just going to have the negative of this integral. So it's essentially just like taking the integral from a lower bound to an upper bound, and then switching the sign when you go from the upper bound down to the lower bound. So if you switch the bounds of integration, then you switch the sign of the result when you integrate. So that's what that little dl means. What about ds? Well, ds is a little vector that describes every little chunk of the surface. So if you were to draw a surface that is actually, that has the boundary C, so I'll draw some kind of little surface. This is like a membrane that sits above this. So if you imagine this is like blowing a bubble, so if you have something like this, if you put this into soapy water, you're going to get a little membrane forming here, and that's one surface that's bounded by this curve. And another surface would be if you started to blow on that, and you got some kind of membrane of soapy water forming like that, that would be another surface. And those two surfaces would actually have the same boundary curve. So the same boundary curve, we can call that C, and then we have multiple surfaces that have that same boundary curve. So what I've done over here is I've drawn that surface S, and we're going to call that S. And what we're going to do is we're going to look at the magnetic field, and we're going to take the magnetic field as it travels through here. So this is the B field. You see, these guys are the B field. And every single point on that surface, you can imagine breaking up the surface into a bunch of little tiles, little tiny rectangular tiles, and each of them would have a normal vector sticking out. So if you imagine my hand is just one portion of the surface, the little normal vector would stick out and it'd be perpendicular to each of those little tiny chunks of the surface. And so what you want to do is you'd want to imagine that this is a little ds sticking out. You'd want to take the dot product of the B field, let's say the B field is here. You want to take the dot product of these two, and then you want to add that up over the entire surface. So that's what's going on over here. So how would you actually compute this? Well, you would parameterize the surface with two parameters, and then you would compute the dot product, and you would take a double integral, depending on what coordinates you want to use. Sometimes Cartesian, sometimes cylindrical, sometimes spherical. How would you compute this guy over here? Well, you'd have to parameterize the curve C. You'd need to find a single parameter that would describe this entire curve. And a line, or some kind of curve that's closed, only needs one parameter, whereas a surface needs two. A volume is going to need three parameters if you want to parameterize the entire thing. So here you're going to end up doing some kind of double integral, and here it's just going to be a single integral, but it's a line integral, and it's a little more complicated because it's a vector field that's being integrated in a three-dimensional curve, some kind of three-dimensional curve. So this works in general for all of these really funky, strange functions, right? So now what we want to do is think about some of the intuitive things. What's actually happening? When we take all of the flux, all of the magnetic flux, we have to take the time derivative and then negate it. And then that's equal to the line integral of the electric field. So the time derivative, that's the change, the rate of change over time. So the electric field, or the circulation of the electric field around that curve, is not due to the magnitude of the magnetic field. It's due to the magnitude of the change in the magnetic field. So changing magnetic fields cause circulations in electric fields. And this negative sign over here, which appears in this form of the equation as well, this negative sign says that that's going to oppose the change in magnetic fields. So the electric field, that's going to be circulating, and it's going to act to oppose the change in the magnetic field. That is summarized in Lenz's law, and that is a qualitative observation. Right? We have a qualitative observation here. Now what we're going to do is we're going to use this theorem over here, Stokes Theorem, and we have another video on Stokes Theorem which you can check out as well. And we're going to use Stokes Theorem to turn this integral expression into a differential expression. And that differential expression is going to use the del operator and a cross product. And whenever you see a del operator and a cross product, you have to think that is curl. That is how stuff is rotating around in three dimensions. And this is a vector quantity. That's why we have to take the dot product with another vector quantity to get a scalar. Right? Because this is a scalar and this is also a scalar. But to get a scalar from two vectors, you've got to take the dot product. If you just take the cross product between two vectors, you're going to get another vector that's mutually perpendicular to both of those ones. So now what we want to do is I'll apply this Stokes theorem to this, and then we can actually do the conversion. And then we'll come back to some more intuition behind Faraday's law of induction. So first of all, we can see that we have this guy over here. This is a line integral. And if we look at Stokes theorem, we've got a line integral over here, and that's equivalent to a surface integral of the curl of the vector field. So this is some general vector field f, and what we're going to do is we're going to apply that to the specific vector field, which is the electric field. So let's do that. Let's make this change. Let's set this guy equal to that guy. So what I'm going to do is I'm going to say my left-hand side, I'm going to set that equal to, let me just write it down, the surface integral over S, and then we're going to take the curl of the electric field. So I'll take the curl, and then I'm going to take the dot product with that infinitesimal ds, which is the little vector that's perpendicular to the surface. And then I'm going to set that equal to, now I'm not going to write this yet. What I'm going to do is, let me just erase this little thing over here. What I'm going to do is I'm going to set this thing equal to a little manipulation. I'm going to use some laws from the fundamental theorem of calculus. I'm going to move this derivative inside the integral. So I'm going to do some differentiation under the integral. I'm going to move this inside here. And if you're familiar with some of this multivariate vector calculus, you'd realize that this has to turn into a partial derivative when it comes inside and acts on the B field, on this B vector. So what is it going to be? What we're going to have is, I'll keep the minus sign outside for now. We're going to have a surface integral, the minus sign at the front, and then we'll move this in, and we'll have partial derivative of the B field with respect to time, and we're going to dot with the ds. And now we might be seeing something, you might be able to recognize something. What do you have inside here? Well, inside you have the curl of the electric field, and inside here you have a partial derivative with respect to the magnetic field. And they're both inside the same thing. You've got a surface integral and a surface integral. So what can we do? We can use the property of linearity, and we can get all of that onto one side and smush them all together. So let's do that. So let's move this onto that side. And if we move this onto the other side, it's the same as adding this to both sides, right? So we'll get rid of that negative sign. And what we're going to get is the surface integral of, I'm going to do some big brackets. We're going to move that to this side, and then we can, because it's the same integral, we can put them all inside of the integrand. So we'll have the curl of the electric field plus, right, it's a plus now, the partial derivative of the magnetic field with respect to time. And I'll take the dot product ds. And that's equal to 0. Right? All of this is equal to 0. Now, I want you to be comfortable with the step going from here to here. Right? So what did we actually do? We just moved this to the other side, and then you can think of it as the integral ate everything. Right? There was two separate integrals, and because it's the same type of integral, it's a surface integral, over the same surface S, we can just absorb them all in together. And that's because of the property of linearity. That's the property that integrals actually obey. Now what we can do is we can say, okay, this is all equal to 0, and if the entire integral is equal to 0, that actually implies that the integrand, everything inside here, has to be equal to 0 as well. So we can go ahead and set this equal to 0. So we know that this guy plus this guy, they have to equal sign, 0. And now we can simply just move this guy to the other side, and I'll write this down here. Ooh, this guy. And here's what we have. The curl, you can see the del operator, also known as nabla, acting with the cross product on the electric field. That's equal to minus the partial derivative with respect to time of the magnetic field. And these are all vector quantities. You can see that we needed a vector quantity over here dotted with another vector quantity, and that gave us a scalar, because 0 is a scalar. So all the vectors and scalars, they corroborate with each other, and that's consistent. So this over here is the differential form of the Maxwell-Faraday equation. So this is, you can think of it as the third one of Maxwell's equations in differential form. So I'll put a little box around it. Now, let's have a look at this interpretation and compare them intuitively using this diagram that we actually talked about before. So this, imagine this surface that's it's got this boundary curve C. Now, let's have a look at, first of all, this interpretation of what's going on, and then we'll have a look at that interpretation. When is the integral form more useful? The integral form is more useful if you have to actually compute a real-world scenario where you have some kind of surface or some kind of little curve in 3D space. If you know the parameterization of one of these ones, then you can go ahead and actually compute the other one. So you know that if there's a changing flux, if the flux is changing with respect to time, there's definitely going to be some kind of circulation of the electric field. And you also know that if there's a circulation of the electric field, you're going to have a change in the magnetic flux. That's what's going to happen. So it's not just a one-way law. A change in the flux with respect to time causes a change in the circulation of the electric field, and a change in the circulation of the electric field causes a change in the magnetic flux. So that's one of the observations that Faraday actually made. That electric fields and magnetic fields, they talk to each other. They trigger each other. Electric fields can trigger changes. If you spin electric fields around, you can trigger changes in the magnetic flux. And if you provide some magnetic flux, then you can actually trigger electric fields to move around. And what did he actually call this? He called this the electromotive force, as we said before. And that's this EMF. Because what Faraday noticed is, in those little wires, he noticed that the charges were being pushed around. So he thought, okay, there must be a force that's pushing these charges along. And now with modern physics and quantum mechanics, we actually know it's not as simple as a force pushing these charges along, but instead it's something like a voltage, right? There's a voltage, and that voltage is what causes the charge carriers, which are electrons, in a wire to move around. And they're not actually the positive charges. The positive charges aren't moving. They're in the nucleus. The negative charges, the electrons, they are actually what's moving. But our conventions for current are the opposite. We're looking at positive charges moving. So the lack of electrons, that's what we actually consider when we're doing our calculations. And what we want to consider over here is, what is the intuitive feeling for it? So we know that electric fields and magnetic fields are related. They can cause each other with this relationship over here. But what is this? You can think of this as how much circulation is flowing around a wire. You can think of it as a wire. And you can think of this as how much a magnetic field is changing and how much the flux is changing through a surface. So here's a real-world example. Imagine if we had a coil of wire and we brought a bar magnet close and we moved it in and out. If we moved the bar magnet in and out like this, what would happen? If the bar magnet was actually constant, if it wasn't moving, there would be no change in the flux. The flux would be constant, so there wouldn't be any circulation. But if we started moving the bar magnet up and down and back and forward, what would happen? Well, what would happen is we would actually have a circulation because there's a changing magnetic flux. Now, why is this important? Well, this is actually one of the principles behind how electric motors work. So electric motors work because you have induction, right? That's what an induction motor does. If you have some kind of changing magnetic flux, you can actually generate electricity. And also, if you have electricity, you can generate physical motion. That's one of the ways of converting electrical power to mechanical power. And that's how a lot of turbines and dynamos work. So it's a way of moving an object and then generating electrical power, or using electrical power to move objects. So this is absolutely essential for the modern world. Electromagnetism is one of the building blocks as a classical theory for modern technology. So let's do a quick summary of what we actually did in this video. We took Faraday's law of induction, or the Maxwell-Faraday equation, and we started off in integral form. We had to look at what the integral form physically means. Then we used Stokes theorem, which is a theorem in vector calculus, and we applied Stokes theorem over here to turn this line integral into a surface integral of the curl. And then we used a little trick of differentiation under the integral. We grouped together some terms which shared the same surface, right? They're integrals over the same surface S, and that was possible because of linearity. We're allowed to do that. And then we realize this implication that if the entire integral is equal to 0, then what does that imply for the inside of the integral, or the integrand? Well, the integrand has to be 0 as well. And so if this is 0, we can just move this guy to the other side, and we have that the curl of the electric field is negative of the partial derivative with respect to time of the magnetic field. So we've talked about what this side means and what this side means, but what about these guys? What do these guys actually mean? Curl is a way to quantify rotation in a vector field. So if you imagine that if you put an oar into some water and it had like eddies and currents flowing, what would happen is the oar would rotate, right? If you put a paddle on the side of a boat and there's vortices in the water, it's going to rotate. In the exact same way, if you have an electric field, if you have a vector field in 3D space, and there's arrows pointing everywhere, if those arrows point and cause something to rotate, then you have curl. And curl is a vector quantity. This is a vector quantity because it's a cross product. And this guy over here, this is the del operator. So the curl is going to point in some direction. You imagine curl is spinning around. At that point, the curl is in a certain direction. It's represented by a vector. It's got I, j, k. It's got 3 components. It's a 3-dimensional vector. And we know that this is exactly the same as how the magnetic field changes at that point, with a negative sign at the front. So it's got the negative sign of the curl, this change in magnetic field. And you can see that this is actually expressing a very similar phenomenon to this. Just the integral form is concerned with an entire surface and an entire loop, or an entire curve that bounds that surface. And this differential form is just concerned with one point. And also, this form is easier to manipulate when you're looking at theoretical understandings of Maxwell's equations. So those are the two forms that are commonly presented for the Maxwell-Faraday equation. And I want you to take away from this video, what does it actually mean to have a flux through a surface? And what does that mean for the circulation around the boundary curve? And what does that mean for physical laws, particularly the Faraday's law of induction?